Thank you.
Okay. Well, thanks a lot for having me here, even remotely, and sorry for not being there. The idea of this contribution is really to show a summary of the activities we did on work package 4. There are to do with source detection and the enhanced stacked catalog. So after this very nice talk by Iris, I don't think I have any doubts that you know all of this is about. I just would like to stress that historically, the source detection method for XMM Newton observations was developed to deal with single observations. And it's only because of e-detected stack and the idea of getting more from sky areas that were observed repeatedly that we have now to deal with this problem, let's say, of stacking multiple observations and having to deal with this problem of having a large number of degrees of freedom during fitting. So the idea behind XMM Newton, XMM to Athena work package 4 is really to try finding out if we could do better with the spectral mode now that Iris introduced. And us in work package 4, we were tasked with the redesign of EML Detect, now called EML Detect ESC, testing and validation, and in particular, we were delivering 2 pilot catalogs and documentation for all that. Okay, so for those 2 pilot catalogs, they were selected from the same pool of over 13,000 observations that consist of for XMM DR13. For both pilot catalogs, the observations were selected in a similar way. First, for the catalog of 4.3 that was delivered in March last year, we wanted to select 300 stacks with where the 3 cameras of XMM operated in full frame mode with a low background level, large overlap between epochs. And we required for this first stacked catalog only stacks of size within 2 and 18. We processed the data with the software version 0.3, which you will see in my slides later on. So here I'm pointing out. And for our next deliverable, D4.4, produced in November last year, we analyzed the same 300 stacks with an improved version of the software, EML Detect ESC 0.4, and complemented this data sample with 300 observations that were non-overlapping, so individual observations from XMM. We applied very similar criteria to select those observations, but required a minimum exposure of 10 kiloseconds to avoid very empty fields. And we also applied some screening to kind of get rid of fields that are known to provide lots of spurious sources, for instance. A third data set that was used to validate and test the software, the new software, is to do with 60 simulations of the Chandra Deep Field South. So for this, we use the 6th software and ready-to-use input catalogs, so-called SINPUT catalogs, that are also provided by the 60 team. So those catalogs include about 700 point sources, AGN-like, with a power law spectrum, but also include extended sources to mimic clusters and galaxies of different redshifts, and a large-scale diffusion emission. for those simulations, we wanted to mimic the setup of real XMM observations of the CDFS, in particular from a large program. And we required observations that were very long for this first test. So over 100 kiloseconds. So these observations, we just mimic the setup, the pointing duration, and so on. And what we produced was a set of 10 stacks with a stack size incrementally increasing from 1 to 10, producing 55 simulations with 60. These include PN, MOS1, and MOS2 for each observation. I have a slide here to say that, well, 60 is a very powerful piece of software in one way, because it's very customizable, if I can say this word. We can with the software try to reproduce many different type of instrumental setups. But it has a 60 in its current version. It has its downside also, that it doesn't work out of the box for XMM Newton in particular, especially if your purpose is to do source detection. So for this work, we are very much in debt to Angel, who is from Athens, that provided us with many shortcuts and tips how to correct the event files post-simulation in order to have them in a workable situation for stack detection. Okay. Here I show some results of those CDFS simulations. Those bar plots show the number of detect sources. Here on the left is a comparison between EML detect ESC, so the new software in blue, against that of public EML detect. For the number of sources on the left, and on the right is the number of sources that we recover from the input catalog as a function of stack size. And we see that the new software is doing fairly well, always detecting more sources than even the sources that we know to be really non-spurious. So these are real detections. Here on this slide, I show a comparison of fluxes from the recovered sources. On the left is for classical mode, on the right for spectral mode. I have to say that this comparison is not very fair for classical mode, because, as you know, in classical mode, we have what we detect or what we are fitting are rates, and then we convert those rates to flux using a given ECF. And a bit by, let's say, an accident, the input files that we use for the simulations adopt a spectrum shape that is very different from that assumed by the catalog in classical mode. So we see that in classical mode, the flux of the sources are very systematically higher than the input catalog. But we see as well that in spectral mode, the new software reproduces the flux of the input very well. The different color shows that the effect of stacking more observations in your analysis, in your catalog. Sorry. So this next slide shows, well, something that I would like to highlight from the tests that we've been making. First, for the CDFS simulations. On the left, it is the distribution of detection likelihood of the new software, so the new catalog, in comparison to the classical mode in red. And on the right, for the positional error, the distribution of positional errors for the sources of the catalogs. And these are only the sources that are recovered in both methods, so that we know not to be spurious. We see on the left that we have this better dealing of the detection likelihood that was expected by design from the method, but we also see on the right that the spectral mode sources in spectral mode have a larger positional error than in classical mode. We see the same sort of result for our pilot catalogs, D4.3 and D4.4. Again, in red for classical, in blue for spectral. And we see the same sort of effect. The next slide shows how well we can recover the spectral parameters of the sources. Here, based on the CDFS simulations, we have their spectral parameters from input. All sources have the same spectral shape. And we see the different histograms in different colors showing the results as a function of detection likelihood. So in 3 sections of detection likelihood values. So in red are the very well detected sources, and we see for those for this quantile, we recover the spectral parameters very well. Whereas in blue, which is the sources with the lowest detection likelihood, so the very faint sources, more poorly determined parameters, indeed have a distribution that is fairly poor, in particular showing a large number of sources that are pegged, let's say, in the extremes of the parameter space. Here we see the same effect, and also something else that now the new software can provide for the sources of the catalog, which is the errors on the spectral parameters. Here on the left, I show the recovered sources from the CDFS again. I scatter with their error bars, showing the photon index as a function of column density. And on the right, I select sources that have well-defined errors on the parameters. So we get rid of these sources with fairly poor spectral parameters determined, those that are pegged on the extremes of the parameter space. Talking about this pegging percentage, so this in the pilot catalogs, D4.3 and D4.4, those sources are consist of a significant fraction of the catalog of the detections, about 1/3 of all detections. And we tried from those 2 catalogs, try to improve the code in order to see if we could, by implementing in particular different procedures in the fitting routines, in order to see if we could determine the parameters of the source data. We do get an improvement on the fraction of pegged sources, as shown in this table here, as a function of detection likelihood, but we can't get rid of them completely. And we see from the CDFS simulations that those sources exist. The sources that are faint will more easily get pegged parameters, so the fraction of sources with pegged parameters increase among faint sources. But even more importantly, perhaps, is that this fraction can be very high for complex fields, let's say those that are either very crowded or are very much affected by bright and diffuse background emission, as shown in the figure here for the case of the supernova remnant W49b, which is the worst affected by pegging. About 74% of the sources were pegged in our first version of the catalog. For the simulations, we see that this fraction is much smaller. This is an effect of the simplified conditions of our simulations, for sure. And we also do not see a trend on stack size for this issue. So this is a bit of a summary. We can see with our test and validation phase in XMM to Athena that the new method does provide a catalog that is more sensitive. We can trust, in general, the parameters of the sources. We can characterize the sources well and their errors. We also do well in terms of runtime in comparison to the classical mode, especially for very long stacked, very long, I mean, stacks with many components. We can now quantify in a proper way the source contamination as a function of detection likelihood. We would like to know the point at which stacking observations do not give us any benefit anymore. And we can now, especially with the simulations, do a better quantification on the theoretical agreement of the catalog with the statistical framework that was designed for the method. What would you like to understand and address is this?
Adriana, can you?
Yes.
Okay, yeah. So I think you have to wrap it up. Sorry. I think
yes, it's already the end.
Okay.
Other
yeah,
things.
Thank you.
Yes, so I would just say, just in general, we would like to address or understand better the fact that the new method gives us sources with larger positional errors, and what we could do in order to deal with the sources that have spectral parameters. So thanks a lot for your attention, and please ask questions.
Hi, this is Phil Evans. I was going to say BBC News just for fun, but actually University of Leicester. So thank you to you and indeed to Iris for two very, very interesting talks on what looks like some fantastic news. I think my question might have been covered on your work to be done. So I'm not sure. What I would really love to see from I love a good simulation and this using these CDFS South images to quantify your performance looks brilliant. I'd love to see essentially a plot of false positive fraction as a function of detection likelihood, and in an ideal world broken down by number of stacks, because it looked in one of your early plots like the false positive rate was a lot higher for 2 or 3 stacks. If you go right back to, keep going back, that one there. So if I'm comparing the left and right, it looks to me like there's a big difference with more on the left than there are on the right, and between about 2 to 3 stacks, which is intriguing. So do you have a plan? I think it was on there, but do you have a plan to produce for us this kind of quantification of how the spurious source fraction depends upon detection likelihood?
Well, I think this is definitely something that we want to have with the simulations. We can do a quantification of that, and that's definitely for our next steps. So now that we have a setup working.
Cool, thank you.
Questions? And if yes, there.
Norbert Schuttle speaking. I was surprised the Chandra Deep Field South was, I think, selected one of the field because of the low NH value it has. And in the simulation, most sources have a very high NH value.
Yeah, that's unfortunately because we were trying to simplify by using the files that were provided by 60. We use those files, but the fact is that they are not very well documented. And so in order to get the parameters from those files, we have to pretty much do a simulation, long simulation, and derive the parameters from there. And yes, it is a surprise that they used for the AGN spectra, something that is more like the Kraft spectrum. So column density that is much larger than in the value in the direction of the CDFS. So this is something that we definitely can change for the next version of simulations. But I think in the end, we were just trying to see how well we were going to reproduce whatever we were simulating, not really having something that is the CDFS. It's just trying to be as realistic as possible, but the spectral shape was indeed not ideal.